here I want to give you some tips on solving problem 456 using ANSYS for the homework. This is a transient conduction problem, so you have to drag transient thermal into the project page, and that's going to solve the unsteady or the transient heat conduction equation. And for engineering data, you are given K and also alpha. So what I did was I assumed a reasonable value for the density and back calculated the specific heat to get the the given alpha. Now, as you change density and correspondingly at the specific heat, your results might change a bit, and it's good to check how sensitive it's going to be. I haven't done that. And we're doing this as 2D axisymmetric. So right at the start, make sure you set analysis type to 2D. And if you go under model, and then you need to create the 2D geometry. So if I go to my model, and actually let me adjust. I was playing around with this. So let me get rid of that. And if I looked at my geometry, okay, it's just a rectangle. And if I highlight global coordinate system, you see that the rectangle needs to be centered. The left lower corner needs to be centered at the origin. And this is the axial direction, and this is the radial. Okay, so interpret x as radial and y as axial. And you need to, under geometry, set 2D behavior to axisymmetric. And that's going to use the, switch to the cylindrical coordinate system and use the cylindrical version of the transient conduction equation as discussed in the ANSYS lecture. And make sure you have assigned the material properties so that the constants in the governing equation are the right ones. And for mesh, I used, and I said edge sizings and a face sizing. And for edge sizings, I used hard. And if you look at my mesh, you see I used only one division in this direction because you don't expect any variation in the axial direction in this problem. It's really a 1D problem that we are solving as 2D. And if you want to remind yourself how to create the mesh geometry, etc., you can go to my online course. So go to edx.org, search for ANSYS. Let me type that in right, and go to this course. And if once you're signed into EDX, you can open the course, go to the course tab, and 2D conduction is the module that you want. And for instance, if you go to the geometry step, it shows you, how to create the rectangle. The meshing goes over the meshing steps and so on. So that's where you can review how to, how to do these things in ANSYS. Okay, going down, you set the initial temperature because this is an initial value problem. So you need the initial temperature. And then you set the boundary conditions. There's only one boundary condition to set, convection. Because here this is insulated, and that is the default. And here, you have the axial symmetry, which is also imposed under the hood. So the other boundary conditions are the defaults, and we don't need to change it. And here, one difference in transient conduction is you need to come and change, set analysis settings. So you need to give it how long you want to integrate. So here I've given it 5,000 seconds. And you can start with auto time stepping to program controlled. And here, the default is all time points, store results at all time points. And you have to be careful because you can get a lot of time points. I've had this issue, and you'll get these huge data files. So start off with a small step n time and solve your problem. with the auto time stepping. And then I've put in a temperature probe. Okay, so I'm probing the temperature here versus time. That's on the surface. And again, if you go to the online course and go to the numerical results section, I have a video on how to probe the temperature. And so you'll get, in the unsteady case, okay, you will get at this location, you will get time versus temperature. And you can see, you know, it's taken only like 14 time steps to get to 5,000 seconds. And that might be the time steps might be too large. And really, it's a good, it can be, my experience has been that your results can be quite dependent on the time step. So you can go to analysis settings, change this to on, which will let me, play around with the initial time step, etc. So let's say I set the maximum time step to 50 and the initial and the minimum time step to 5 seconds. Then if I resolve and look at the temperature probe, let's see, this is, I'll minimize that. So now you can see that, it used 103 time steps to get to 5,000, and the final temperature is slightly different. And you can play around with that. And one thing to keep in mind is you don't want to usually save all the nodal temperatures at all the time points. So go to analysis settings and select this to equally spaced. And let's say, I save it at 40 time points. So now if I go to temperature probe and look at the table, let me minimize that. Okay, see, now I have only 40 time points. If the end result is the same, so the results don't change. The values, the time values at which you're getting the results will be different, and it'll use interpolation as necessary. So you can do that. Okay, I like to use for under analysis settings. I like to use fewer time points and then go higher if necessary. And then I can also look at the temperature variation. Let me minimize that at any time. So I can enter a time here. So if I say 1,000 seconds and I just say retrieve this result, and it'll give me the temperature variation at 1,000 seconds. And I can do a 3D visualization of this. This is pure visualization. To do that, I need to go over here, go to Tools, Options, go to Appearance, turn on Beta Options, then go here, highlight Model, add symmetry, change symmetry to 2D Axisymmetric, and I'll say 28 repeats, each repeat being 10 degrees. And now when I go and look at my temperature distribution, if I get a three-dimensional view, you can see this has been repeated 28 times. And so that gives you a nice three-dimensional view of the temperature variation in the log.